In this video, we will make the summary of the important points that you learned about Laplace transform. The basic that you learned in Mathematics 1, such as integration by part, factoring, computing the square, partial fraction, is very important in solving the Laplace transform. Please make sure you master it, and then you must know how to use the Laplace transform definition to find the Laplace transform. So L curve is equal to the Laplace transform. So if you want to transform your ft to capital Fx, so this is the Laplace domain, this is the time domain, and the definition is, so you have your ft, you need to multiply with exponential negative xt, and then integrate it with respect to 0 to infinity. So this one with respect to dt. So this is the Laplace transform definition, where your s is a complex number, which is sigma plus I omega. You must also familiar with the table and the corresponding concept in order to perform the Laplace transform and also the inverse Laplace transform. So this is the first part of the table, where you transform the ft to be this function, and then you get the fx here. So this is the corresponding concept. This is the second part of the table, and if you master all the concepts, so in total you have 12, and you will find that it will be easy for you to apply Laplace transform and inverse Laplace transform in most of the cases. For the first three concepts, we show you that when we apply the definition for constant, then you should be able to obtain the fx to be this. So remember this format. So when you have any constant, then your fx is equal to c over x. Then for the exponential, so when you have any exponential, your format will be 1 over x minus a. So be careful, when your a is positive, you have negative 5 here. When your a is negative 5, then you will have positive 5 here. So lastly is polynomial. So polynomial is in this format. If it's just t, then you will have 1 over x squared based on this formula. If you have t squared, then you will have 2 over x power 3. If you have t power 3, then you will have 3 multiplied 2, which is 3 factorial, divided by x power 4, and so on. So you can see the pattern where if you have x power something at the bottom, it will be a polynomial function t. And if you have x minus something, it will be an exponential function. And if you only have x, it will be a constant. Checking the denominator for the fx is very useful for you to do the inverse Laplace transform. In the concept 4, you have the linearity property. So this is the formula. By using this formula, instead of performing the definition of the Laplace transform, so we can obtain the Laplace transform for sine and cos here by just taking the Laplace transform for exponential. And we see the link, okay? So it will be same with Laplace transform for cos and I sine angle. So your Laplace transform for sine will be the imaginary part for the answer here, and your Laplace transform for cos will be the real part. So you should be able to obtain this answer. And if you want to take the inverse Laplace transform from fx to ft, if you have x squared plus omega squared here, then it will be either sine or cosine. If you have x squared minus omega squared here, then you will have hyperbolic sine or cosine. If the numerator is constant omega at the top, it will be either sine or hyperbolic sine. Then if you have the variable x at the top, then you will have cos or hyperbolic cos. In concept 5, you have the s shift if you multiply the exponential in the time domain. In concept 10, if you multiply the exponential negative ax in the Laplace domain, you will have the time shift multiplied with the unit step function. So this is the formula when you take the Laplace transform for exponential multiplied with the cos omega t. So cos omega t, you know that your answer is this. When you take the Laplace transform for cos omega t, you should obtain this. When you multiply exponential function in the time domain, then you will have S shift, where your S here will be replaced by x equal to x minus a. So after you substitute x minus a inside, you should be able to obtain this result. So this is the Laplace transform for this term. When you take the Laplace transform for unit step function, then you obtain 1 over x exponential negative ax. So without this term, then without the exponential. Because Laplace transform for 1, you obtain 1 over x. So if you have unit step function t minus a, you will have additional term for the exponential negative ax. So if your constant is 5 here, so you will have 5 over x. Lastly, you need to be careful when you take the Laplace transform for this term. So this function must be ft minus pi over 2. Because you have unit step t minus pi over 2, it must be the same here. But if you look at this term, cos t is not in t minus pi over 2 function. Therefore, you need to convert the cos t into sin t minus pi over 2 function. So in this case, your sine function, if you without this term, your sine function is the ft minus pi over 2. You need to find your ft function from it, which is the negative sine t. And then from here, find the Laplace transform for it. Your fx is equal to negative 1 over x squared plus 1. So this term is your fx. And then due to the unit step function here, t minus pi over 2, you know that your a is equal to pi over 2. Therefore, you can substitute inside the formula for here. So substitute pi over 2 here, you obtain exponential negative pi over 2x. So Laplace transform is very useful because it can convert differentiation and integration into multiplication or division. So you can see that when you multiply t with your function ft, you obtain differentiation with respect to x with a negative dash. So if you multiply x here, so let's say you have x fx minus with your f0. So this is df over dt. So for the third case, if you have ft divided by t, then you need to integrate from x to infinity, because we know for s is only valid for certain region. So this is called the region of convergence. So if you have integral in time domain, if you take the Laplace transform, you'll be just fx divided with the x. So in ODE, this is very useful. So make sure you know how to differentiate d square f over dt square. So means you differentiate this again. So you need to multiply with x. So you have x squared minus with x minus with 1. And then over here must be capital Fx. So this is initial condition F0. And this is the initial condition as well, F prime 0. So this is the result when you take the Laplace transform of the derivative. So this is the first derivative, this is the second derivative. So this is the delta function, which means the impulse function. When you perform the definition, you obtain this. So you want to convert delta function t minus a multiply with your exponential negative xt and integrate with respect to dt from 0 to infinity. So due to the shifting property, you will obtain okay, the delta function will shift out the exponential negative xt, okay, at t equal to a. So this is the result. The formula for the delta function and the unit step function is almost similar, where you can see you have additional 1 over x term here, indicate it's a unit step function. If it's just a exponential function, it will be a delta function. So when your a is equal to 0, so you just have delta t. In this case, you obtain 0, which is equal to 1. If your a is 0 for the ut function, then your exponential is equal to 1, and 1 multiplied 1 over x gives you 1 over x. Lastly, in the concept 12, we learn about the convolution, which can be represented by this symbol. So this symbol consists of summation and multiplication, where you can see in this definition for the convolution, you see the multiplication between f tau and gt minus tau, and the summation here indicating by the integration, where the integration formula can be equal to the summation formula here. So performing the integration by using the convolution is time consuming. So if we don't want to perform this, we can perform the fx, where you take the Laplace transform for the ft, then you can easily get the fx. So to obtain the gx here, you perform the Laplace transform for gt, then you obtain the gx, and you multiply them together. So in order to obtain this answer, it will be equal to inverse Laplace transform. So for your capital fx here, multiply with your capital gx here. So this is the same answer by performing this, but this is much easy and simple. In simple, instead of performing the convolution operation here, which is complicated and time consuming, we can perform the multiplication in Laplace domain.